So hi everyone, I apologize in advance because Michele has asked me to give the talk in English. So it feels weird for me because Bologna is my hometown. But to compensate, I try my best to speak English with a very strong Bolognese accent. Okay? So I'm Stefano Zacchiroli. In real life, let's say I'm a professor of computer science at the University of Paris. I've been a free software activist for maybe 20 years now. But I'm here today to talk to you about the Software Heritage Project, of which I'm the current co-founder and CTO. And this project is about archiving all source code that you can find on the internet forever, nothing short of that. So let's start with some comments about why we're doing this. So software, we are all basically dealing with software on a professional basis. Some of you will be developers, some of you will be recognize themselves as DevOps, some of you as operations people, but software is part of our life, of our professional lives. Okay? But even for people that do not deal with software in any professional capacity, sorry, I need to start my timer. Yeah, much better. So even for people that do not deal with software as a professional thing, their lives are completely controlled by software. Okay, so these days it's very hard to drive your car to come here without dealing with software, or to file your taxes, or even to just survive in case you have some medical devices implanted in your body that are almost certainly controlled by software. So software is everywhere, controls our lives, and interesting enough, more and more in later year, you will find that but there are a lot of software that controls our life, which is actually free software, or free and open source software if you prefer. So that parts of that software that control our lives are freely available on the internet and can be actually read, shared, and modified by most of us that have the competence and the capacity to do so. Not all of it is free software, but a good part of it is. So, and this thing, which we call source code, and we know very well what is due to our profession, is actually a pretty special thing. So it's a kind of information that is new, is an all-time new in human history, and it's actually knowledge that is both readable and understandable by people and executable by machines. So this is very new. The only approximation of this you find in human history is kind of music scores, okay, which have both some parts that are meant to be played by instruments, some parts that are meant to be read and understood by people. But source code is way more. So if you look at source code pieces that you find on the internet, like a bit of code of Quake 2 or a bit of code of the network queues that's implemented in the Linux kernel, you find in there very smart information, very smart approaches to solving hard problems. For instance, in Quake 2, you will find some very efficient state-of-the-art algorithms to do rendering of polygons in a 3D environment. In network queues of Linux, you will find very efficient protocols to do packet delivery in time-efficient ways. And that is actually more than the fact that you can actually run those algorithms. Okay? This is something that people can look at, well, developers can look at, and understand there is some value there, even if you do not run them. Okay? This has been recognized in the history of software and computer science many years ago. And there are some very interesting observations about that programs are actually written mostly for people to be read and modified and executed and compiled later than for machine to be just executed. So there is important knowledge in source code which is more than the functional value of software itself. And all of this is actually the software commons of our lives, okay, of our generation. So the commons, in Italian we would say bene comune, is actually stuff that is freely accessible to everyone to be used and is not owned by any one individual or any one entity that can exclude others from using it. And the software commons is all the body of software which is freely accessible to all of us, can be freely used, modified, and shared without any sort of restriction. So the new commons that we have in our generation is actually the software commons. Okay? And this is something we need to take care of, and we need to actually make sure that get passed on to future generations as our technical cultural heritage, if you want. So are we taking good care of this body of software? Are we? So there are reasons to be skeptical that we are. So first of all, there is no place where you can go and actually appreciate, actually get a feeling of the size and the amount of these software commons. So software, and specifically software in source code form, is hosted on many different platforms, as it is natural to be, right? So there are different trends. Now, these days, GitHub is cool. 10 years ago, SourceForge was cool. Who knows what will be cool in 20 years from now for hosting source code, right? So you have plenty of different platforms. You have plenty of places where you do distribution of source code. So you can retrieve source code from the original developer of some software. You can retrieve source code from intermediate distributors like Linux distributions or app stores. Okay? And the same amount of software can be distributed by very different channels. Okay? And also, over time, as trends fade and new trends arise, okay, projects will migrate from one platform to another. Many of us are old enough to have witnessed the project that were first posted on some self-hosted CVS, then they moved to SourceForge, then they moved to Google Code because it was really cool at the time, then they moved to GitHub, and who knows where they will go in the future. Okay? So software move around, so that makes it hard to have a single place where you can look for some specific piece of source code, okay? Or for just browsing what exists, or to get an idea of how big it is, our software comes. Second observation, source code is actually quite fragile. All digital information is fragile. Many people are talking about the digital dark age, saying that we will be the first generation that will have no memories, because it's much easier to destroy your collection of digital pictures by mistake than it was to destroy your collection of physically printed pictures. And this applies to all sorts of digital information. Okay? And specifically, it applies to source code as well. Okay? So we have seen over the past years many reasons for being concerned about the preservation of source code, which is currently freely available on the internet. For instance, we have seen deliberate attacks that has been, destroyed entire code hosting platform. There is an interesting story about Code Spaces that I encourage you to look up. It's been a company that was doing source code hosting, and there's been essentially crackers to control of their cloud management dashboard, and started to say, unless you pay us 10,000 K, we will delete your volume 1. Okay? And this time they didn't pay and started deleting each storage volume they were using. And you can ask, sure, but didn't they have backup? Yes, they did have backups, but the backups were on the same cloud platform. So they even destroyed the backups, and of course the company went out of business. So this might happen. So you may have attacks that destroy completely the entire collection of source code. You may have business-driven decision that ends up shutting down services that are hosting source code, right? So Google Code, for instance. Google decided that they didn't have an interest anymore in doing, code hosting, and so they decided to just shut down Google Code. And first, they shut down the access to the version control system and offered ways to actually retrieve it in read-only format. And then they started hosting only tarbles or zip files of software releases. At some point, they will just shut it down completely. Okay, they've given plenty of time to migrate away, but do we know if all the source code that was hosted on Google Code is actually migrated away or not before the service will definitely shut down? We actually don't. And GitOrters, same story. And of course, you have also the natural reasons for which source code might disappear. Like my friends at the FSF have like the basement full of tapes and disks, physical disks, very old version of GNU-tar. And of course, those are literally bit rotting in their basement. Okay? So there are plenty of reasons why we might end up losing software. And the question is, where do you go if a specific repository is taken down from GitHub or GitLab.com, or if the entire service goes away? If a web page goes away, you usually can go to the Wayback Machine to retrieve old versions of that page. Where do you go if a specific version of a Git repository or any other version control system repository disappears? You might say, well, these days we all have distributed version control systems, so someone will have a copy on their disk. That's true, but good luck finding that person that has the last Git clone or the last Git pull of a specific repository. And last but not least, so this is my pet peeve as an academic, we don't have a place where we actually can do large-scale research on the entire source code that is available today for everybody. Okay? So if you are a scientist and you do like astrophysics, you want to do some fancy experiment, you can go to in the desert of Chile, Atacama, and you have the very large telescope that scientists around the world can use to make specific use of astrophysics research. If you want to do the same thing on source code, you don't have a place where you can go. You can do large-scale analysis to see how free software developers are doing some things. What are the patterns of development that lead to some specific bugs? Okay? People are doing that kind of research. There is an area of research called mining software repositories, but all of them are doing that using small samples of data extracted from GitHub and hoping they will be representative of what happens in general in software development in the world. So it would be actually very cool for scientists and for software engineers specifically to have a place where you can conduct large-scale experiments on the entire body of software that is freely available for everyone to study. So for all these reasons, we started about, well, the project has been announced about 1 year ago. We started working on it about 3 years ago. It's called Software Heritage. And the goal of the project is actually collecting, preserving, and sharing the total amount of source code that is freely available on the internet. So we retrieve all source code we can find. We store it for archival reasons on the very long term, and we share it with everybody who actually wants to actually retrieve it. So sharing in the sense that if it disappears from somewhere else, you can come to us and you will find copies of that piece of software that you actually cannot find anywhere else anymore. Okay? So the idea of the project is actually to do just this, which is a very big endeavor, but it's just a single thing. So we just want to preserve source code itself. And the idea is to do that in a sort of Unix philosophy kind of way in which we do the archival, the collection and the sharing, and on top of our archive you can build specific applications that serve specific use cases. So I've already mentioned how just the collection part is important for preserving our digital cultural heritage, if you want. I've already mentioned the interest for research, doing on this body of source code. But there are also other interesting use cases for education, for instance. So we are now in the condition to build what is the source book that we can use to train future generation of developers, telling them how specific implementation of algorithms evolve over time. Actually, a pretty cool thing. I'm not saying that just collecting will give you the source book, but collection is something that you do need so that teachers around the world can actually start doing the curation needed for actually creating that source book that will be used to train future generation of developers. And there are also some pretty interesting industrial use cases. So provenance, specifically for free and open source software, is actually a very high kind of business these days, because if you are integrating some version of some free software projects in your product, you actually need to be able to identify the very specific version of the code you're using, because when security vulnerabilities are published, you want to know if your version is affected or not. Or if you just want to know if you actually you've probably done some static analysis on the code with specific tools, you need to know the specific version that has been used. Or for licensing reasons. Okay, there are a bunch of companies doing this kind of work, but all of them actually are redoing the collection and harvesting of publicly available source code. And actually that's a waste of everybody's time. It would be much more efficient to have a single place that is accessible to everyone, that do the collection and does associate some sort of part number of specific version of source code that you can reference that standard part number in all your internal database of information about that software. So we are building the archive, and we are doing our best to make it sure that all these use cases can be implemented, not necessarily by us, by others maybe, on top of the archive itself. And our principle, actually pretty radical in a way, so we believe this mission is actually truly important. It's more important than our project itself. It's a mission we believe is useful for society as a whole. So we're trying to implement it in as open as possible way. So all what we do, all the software we develop ourselves to support the mission of the Software Heritage Project is entirely free and open source software. And also, we try to be as transparent as possible on our operations. So the way we treat data is something we disclose. And of course, it's collaborative development, so everyone can join and help us creating the infrastructure and the software we need to make this work. And we are trying to maximize our chances to be here in the long haul. Okay, so this project to be successful is not a project that should be around for 10 years. It would be entirely pointless. It's a project that to be successful is something that should have reasonable chances of being around hundreds of years from now. Okay, we will not be there anymore, but if this project has been successful, it means we can preserve every single line of source code which is published on the web forever. Of course, it's just a matter of probabilities. Nobody can guarantee that, but we're trying our best to maximize our chances. And part of that is, of course, replication. So even though the archive is meant to be a single logical place, ideally the infrastructure will make it sure that the archive is actually geographically distributed around the world and under the control of different organizations, so that you cannot have a single business decision that actually decide, no, let's shut this down because it's become too costly to maintain the archive. And part of it is actually making sure that the business model of the project is actually entirely non-profit. Not because for-profit businesses are bad, but because they are more prone to change their priorities. So companies can be bought by other companies that have different priorities. We have seen that in free software far too many times. And we believe that a non-profit model will maximize the chances that the goal remains set in the very long term. So this is what we're doing, and this is our principle. So in details, what we are actually doing. So we go after places that are meant to host source code. So that means essentially version control system repositories and source code releases, for instance, tarballs or source package releases from distributions. And when we end up on those places, what we do is that we archive all versions of all files we find in there. So if we end up on a version control system, we will crawl through all the releases in that specific VCS, find all different versions of any file that has ever been committed, and actually archive them. We call this blobs or contents. We archive all commits. Okay? We believe that source code makes sense if you maintain both the code itself and the history of its development. Because you note down stuff in commits that is very important to remember. Why you've made some changes, or references to bugs that you have fixed in that specific version, or who did that, when it happened. Okay? So we also archive all the information we can extract from version control system. And so every single commit and all the metadata associated to a given commit is something we do archive. Same thing for releases. So which commits correspond to specific target releases of the software, we archive all of them. And also, of course, where and when we've found any of this on the internet. So essentially, we want to know where a specific version of sched.c from the Linux kernel has been found, which repository was it, and what was the timestamp at the time, so that we can reconstruct the history of the source code that has been hosted on at a specific place whenever we have visited. Okay? And all this is actually stored in a canonical model, which is independent from specific version control system or from specific packaging formats, okay, so that it's maintainable and evolvable over time. What we do not archive currently is on-page of projects or wikis of projects, backtracking system, issue trackers, code reviews, commentary. We do not archive any of that, or mailing list. And we do agree that all this stuff is very important to reconstruct the state of any specific software development project. But we were trying to focus on a single mission, and our vision is that you already have other people archiving that kind of stuff. For archiving mailing lists, you have Gmail. For archiving website, you have the Internet Archive. Okay? So our idea is that we will play our part in a hypothetical semantic Wikipedia of software, where you can say, we can have people curating the history of development of specific software and saying, this archived here as the source code, this other archived here as the mailing list, this are archived here as the wiki and the website. Okay? So we are trying to make it as easy as possible to reference a specific version of source code we have in our archive. Okay? And the idea is that it can be easy to mix and match those information with archival of other software-related artifacts archived by others. So in terms of architecture, it's a pretty standard search engine-like architecture. So it's a two-tier architecture in which, now I need to point at either of the screen. Does this work? Yeah, okay. So it's a two-tier architecture in which we actually start from specific software parts and from specific hosting places for source code. And you have in there code hosters like GitHub or GitLab.com or specific instances of GitLab or Bitbucket or any other forge you can imagine. You have distributions like Fedora, Debian, Ubuntu, what you have it. And you have also, more and more these days, package repositories. Usually repositories associated to package managers of specific programming languages like CPAN or PyPy or NPM and a bunch of others. Okay, so we currently maintain that list of starting points by hand, and people can suggest more entities to be added there. And periodically, on a scheduling base, driven by a scheduler, we can list all packages, all pieces of software available there. Okay, so we can go and see Debian and say, tell me all the packages you have, or see on GitHub and tell them, give me all the repositories you have. This can be done in a full way, where listing everything, or in an incremental way, listing only the new stuff that has been added since the last time we've been there. And for every single package or repository that we can find, we maintain an abstract entity which is called a software function, okay, associated to a type. So software origin can be something like a Debian source package, or a specific Git repository, or a specific tarball that is get released over time. And again, periodically we go through these places and we do loading of all the information we can find there in our archive. So our archive is a peculiar structure which is fully deduplicated. So if any specific version of any specific file is stored only once, no matter how many different places we have found. Any specific commit, even if it gets pushed to hundreds or thousands of different VCS around the world, is stored only once. So any of the entities I've mentioned before is stored exactly once. So the loading process, what actually does, is that it consults the list of objects available at the specific software origin. It compares with the state of the archive as a whole, not only the state of that repository last time we visited, but with the state of the archive as a whole, and we only add to the archive the new object that we have never seen before, okay, and we will add them to the archive. The different software components we are using here, listers and loaders, depend on what they work. So for instance, we have specific listers for GitHub, for Gitbucket, we have specific loaders for Git or Debian source packages, and more can be easily added for other formats. So the archive itself is actually stored as a two-tier archive again. So it's in part a blob storage, where we only store the content of a specific version of files, and a Merkle DAG. So for those of you who might not be familiar with the Merkle DAG structure, are structures that are typical in cryptography, and are essentially trees of hashes. So in a Merkle tree, you have the leaves of the structure where you have the content of the files. You compute checksum of those contents, and the node up there actually have their identity computed as checksum of where the pointers points to. So here you have 4 blobs. You take the checksum here, and the identifier of each leaves is the checksum of the content. And the nodes up here have actually their identifier that is computed as a checksum of the direct descendants. So essentially what you have is that the top hash depends entirely on the content of the structure itself. This is a very common structure these days. It's the funding structure for blockchains, or for Git itself, or for distributed storage like IPFS. Okay? And this is a structure we use in our archive, except it's not a tree. Okay? It's a DAG, because you have stuff like commits, which you can merge and fork. So you have actually structure that are not strictly speaking a tree, but they are completely acyclic, because otherwise there will be no way to compute the ID of a node. So an example of a node that we store in our Merkle DAG is a revision, or a commit if you want. So this is a specific commit that has been made by a colleague of mine, and you have all the information of the commit itself. You have the directory to which the root directory of the commits, okay, which transitively points to the content of the directory at the time, and you have a bunch of metadata. So what is the parent commit, who is the author, what is the timestamp, and what is the message. So right now, the IDs we are using are compatible with Git, but this is just for convenience. There is no reason why they need to remain so in the long term, but currently that is the case. So all of the IDs in our Merkle DAG are currently compatible with Git itself. So the archive itself is a giant Merkle DAG structure. So you have here the leaves of the structure are the content of the files. Then you have directories pointing to blobs or to other directories. It's similar to what happens in a Unix file system. And then you have revisions that are your commits, which are linked together by the timeline. So each commit is as a parent commit, or maybe multiple parent commit if it is a merge, and can be used by other commits as starting point for forks. Releases are just specifically tagged revisions, okay? And the topmost structure we have in this DAG are actually snapshots. So what is a snapshot? It's a picture of a specific repository we take at a specific time. So we end up visiting a specific Git repository, for instance. We look at where all the branches available points to. We put all this in a single object, and that is a snapshot of that repository, which of course can be the same snapshot of many other Git repositories we find around the net. All this natively deduplicated. So this is implemented in practice as a software stack in which we're using Debian and Puppet for the infrastructure layer, fairly standard stuff. We are storing all the structure of the graph itself in Postgres currently. It's a scale-up setup with a replication using logical and point-in-time recovery, point-in-time backup using Barman. Okay. I'll get to why we're using Postgres in a bit. The architecture, the software architecture is completely event-driven. So we do event dispatching using RabbitMQ. All the software developed itself is essentially Python 3 using PsychoPG to interact with the backend stuff. And for the web front ends, we use Flask and Bootstrap for the user-facing feature. So this is the third-party software we use, and what we have handled in-house is actually the object storage itself. Because at this place, we do not, at this moment in the project history, we do not want to impose any specific object storage technology to downstream mirrors, but there is no reason why you cannot map our object storage on your Ceph or whatever other solution you are using in-house for doing object storage. And then, of course, you have the implementation of the data model itself, plus the listers, the loaders, and the scheduling routine. It's all free software. It's available on our Fabricator Forge, and the license we choose for this, our stuff are either GPL3 for the backend code or AGPL3 for the front-end web stuff. Other stuff, other stack. So we wanted to start with in-house hosting of the data to actually have a credible prototype before going after in-kind sponsor for resources. So right now, the main 2 copies of the archive are actually stored on a high-density storage arrays. So we have 600 terabytes of data using 2 copies of 300 terabytes in a very high-density storage array. We have like some 120 disks, which are not that numerous, but that's what we use currently. And we are starting to have a full mirror on one of our first partners, which is the Azure Cloud. And in there, we are using their object storage, and we are close to have we are about 50% of the object storage has been fully mirrored to Azure. And the idea is that we will use that to make it easy for other mirrors to actually doing mirroring from cloud to clouds, and for running workers that will do batch analysis on all the blob that are installed. So what is in the archive? This is just not a theory. It is a very real archive. So in the archive itself, we already have a full, periodically maintained, up-to-date mirror of GitHub itself. GitHub has been kind enough to start mentioning us in they have a page in which they list people doing archive of GitHub, and they mention us there. We have some experiments. We've done a one-shot injection of the entire history of Debian between 2005 and 2015. Okay? We've done a one-shot instance injection of all the releases of the GNU project at the time of the summer of 2015. We don't have it yet in production to maintain up to date with respect to those source code hosting places, but that is part of our roadmap. And we've also, thanks to collaboration with the archive team and with Google, retrieved full copy of all the source code hosted on Google Code and on Gitorius at the time of the shutdown. So it's not only the tarbles that we retrieved, we retrieved the entire history of all their Git and Merkle repository before the shutdown itself. So there are some numbers. Okay? You have the growth rate. All numbers are about deduplicated objects, right? Unique objects. So the graph on the left is the number of source files. This dates back to January. So if you go on our website, you will see more up-to-date numbers. So we have some more than 3 billion unique file content we have archived. Something like 700 million commits we have archived. And we are tracking more than 50 million projects. So the little bump you see in, well, not so little bump you see in the graph is when we started following also GitHub repository that are declared as forks. So in the beginning, we started cloning only the repository not declared as forks, okay, because it was the fastest way to retrieve different actual content. And then at some point, we started saying, hey, let's track also the others, so we have a bump in there. And you don't have an equivalent bump in the amount of objects because everything is deduplicated, and so the hit ratio when you go after a repository is a fork of a repository you have already forked is actually very high, so you don't have much to the content of the archive itself. It's probably, arguably, the largest archive of source code in existence today, and it's actually growing daily already. So what can you do with that? So we have released about 1 month ago our first web API. And using the web API, what you can do is actually have the equivalent of the Wayback Machines for your repositories. Okay? So you can say, hey, there is a repository I care about. Can you tell me how many times you have visited it? Okay? And can you tell me what was the state of the repository at the time? Or, given a specific visit you have done, where was the master branch pointed to? Okay? You have a full API endpoint index as the address given there, or you can find a reference on our website, of course. And just to make you a quick tour of the API itself. So for instance, let's imagine you are a developer or a user of the high programming language. You want to see, okay, does software heritage track the high programming languages, and in particular their repository on GitHub? So yes, you can go to this address, and we'll tell you, sure, we know about the GitHub repository of high. It's our origin visit number 1. That's just because the high developer is a friend of us, so we use them as a guinea pig. And you can say, okay, let me know how many times you have visited the repository using this second address in there. We'll tell you, sure, there's a number of visits. We'll give you back a list of visits, everyone pointing to a specific URL, which will give you more information about the visit itself. So for instance, visit number 13 of the Highland repository has been done on September last year. And let's have a look at the state of the repository at the time. So you follow the URL for that visit, and you will find a huge mapping between Git branch names and where they were pointing to. So for instance, master branch at the time was pointing to a commit B94 something, and you can have more information by following that path. While the tag 010 was pointing to a tag object, okay? And this is the ID of that tag object. So now you can go further. So given master was pointing to a specific commit, you can have a look at the that commit. Okay, I'm not sure we did the same, but when you end up on a commit, we'll give you the information about the author, the committer, and where the root directory of behind that commit were pointing to at the time. Okay, so here you have a directory. You can go down, see a list of the content of that directory at the time, and at some point, you will reach some actual real content. So you end up on a file which has a specific checksum, and here you will find information about that file. You have a way to retrieve, to have a URL to the actual content of the file, plus some metadata we are computing on a best effort basis, like the type of the file detected with file type, or the programming language, if we recognize it as a source code file, and so on and so forth. There are some limits. So right now there are some pretty severe range limiting in place. So I think you can do something like 120 requests per minute, not more than that. Of course, we basically want to focus our limited resources in adding more features to the archive before putting a lot of energy in maintaining the service as a public service. And block download is not available yet. So essentially you can have now all the metadata but not retrieve the actual content, but this will change in the next few months. So this is the most advanced feature we have for the archive itself. In our roadmap, we have more stuff to be added, of course. So, for instance, it would be nice to have a Git-like browsing interface for web users and do not force them to go through some specific API. So this is actually an important point of our roadmap. And of course, it would be nice to be able to allow people to actually wget of entire releases of software and direct Git clone for software heritage. And that too is planned to happen in the next few months, I would say before the summer. We also added the provenance information to be added. So essentially we will allow people to say, hey, there is a specific file, tell me all the places in the world where you have seen this file and when you have seen it. Okay? This is a big undertaking for a reason that we'll get to in a bit. But it's actually something we want to add as well. And of course, full text search. So wouldn't it be nice to say, hey, tell me all the places where you have the printf function, or maybe something more interesting. Tell me all the places where you have this specific 2 lines of code which correspond to a bug that I want to know where it has to be fixed. And of course, once you have that, the sky's the limit, right? So you can do plenty of stuff once you have all the public available source code in a single place. So, given we are here at the Untitled DevOps conference, so I'm not a professional DevOps, okay? But we have some, so I'm here to start a conversation with you, and I'd like to discuss with you some of the challenges we're facing, and I think will be plenty of interesting information for questions or discussion at the end of the talk. So, of course, scaling is an issue for us, even though this service is not so big. Okay? So we are talking about, I actually skipped an important detail, the size of the archive itself. So currently, it's something like 150 terabytes for the blobs. So the actual content of the files, fully duplicated, is 150 terabytes. And the size of the database itself, where you store all the graph, basically, is something like 6 terabytes in a Postgres database. If you look at this as a graph itself, is a pretty big graph with 5 billion nodes and something like 50 billion edges between those nodes. Okay? And these numbers will become important in a second. So it's big, but it's not that big. It's not YouTube, right? So it's 150 terabytes for people doing hosting of user content. It's not that big, but still, it's actually pretty demanding on downstream mirror operating. So I experienced with the Debian world, in which in Debian we have a large network of volunteer mirrors around the world. But it's not like you can go around the world and say, hey, you have 150 terabytes that you don't use and you can use to mirror this. So that's kind of difficult to ask for. Still, it has some good verification properties. So the archive, by construction, is an append-only archive. So once you have the initial copy, the only addition you get are additions of new files that flow in daily. So you never need to delete stuff or remove stuff or write stuff except for self-healing purposes. So for instance, given everything is addressed by a checksum, you can periodically go through all the objects you've stored, and if you notice that the content of the file does not match the checksum, you know that some bit rot of sort has happened, you can go ask other mirrors on the world, hey, you have a version of this file that is correct? And if so, use it to correct the error you find on your copy. Still, doing some heavy maintenance operation, like if you want to change the keys, will require some substantial resources. So this is a problem we are facing. There is some interesting problem with the size of with the choice of a Merkle DAG model. So we believe it's a very good choice because it's the only way to be able to sustain the fact that software moves around. Okay? And the software will be also in different places. So if you want to scale when software moves around, you need to store everything in a deduplicated way. But it seems that this kind of graph is actually beyond the state of the art of graph databases. So you have graph databases that can scale up to trillion nodes, but usually they can do so on a very specific kind of graphs, that are graphs known as small worlds. So for instance, the graph of the internet itself. So this seems to be optimized for graphs in which you have a very nice 6 or 7 or whatever degree of separation room, which is not the case for our graph. So we've tried some graph databases solution, but they are not scaling to what we're doing. So there are some interesting challenges with this. And some of the queries we want to do are actually pretty hard on this kind of data model. For instance, if you want to know all the places where you have seen a specific file, so you have our graph, you start from the leaves of the graph, you need to find all the roots of that graph that point to specific leaves. That's actually a very computational and infeasible problem if you don't have some way of directly knowing who points to what transitively. So this is something that we're struggling with. So we have some mitigation. So for instance, we have some caches for keeping the mapping, but it's actually very hard to keep up. And of course, you have the challenge of storing full text indexes, because every kind of full text index you might want to have for the content of the file will have basically the same size of the content itself. But then again, the good property there is that all derived data, so it doesn't need to have the same retention policies that you have for the rest of the code. So we are using some cloud-based stuff to do that, but it's actually a good challenge in where you will keep all that stuff in the long run. So this is part of the scaling issues we're facing. And then, of course, there is an issue of operational transparency. So we believe the mission here is pretty important, as I mentioned. It's more important than the success of the project itself. So we are trying to make sure that people can look at what we are doing, okay, and believe that we are doing that in the best possible way, or actually help us out in improving if we are not doing that in the best possible way. So how can you prove that you are doing all you can for preserving source code to actually people using the service? So it's kind of pretty difficult at this scale. So the fact that we are entirely free software and the fact that we are running this as a non-profit business for us is part of the answer, but it is not enough by any means. So ideally, what you would like to add here is that every change you do to any content you store in your archive is actually logged, and you keep essentially a full version of your entire database. So of course, we know how to do that when you change the structure of the DB, right? You keep your upgrade SQL statements and you store them somewhere. But what if you change completely the structure of the archive? What if tomorrow we move from to a different DB solution? Ideally, you want to keep all old version of all your data so that you can go back and recover from some mistakes. So we are doing some of it. For instance, in keeping up with GitHub updates, we store all the pack files, which are the low-level object sent by Git over the wire when you do a Git pull. We store all of them in addition to the change to the archive itself. So that if we end up discovering a bug in our Git loading structure, we can retrieve a pack file and redo the injection. But that, of course, doesn't scale. So here, I think there is a real challenge in which how you keep a 100 terabytes archive, a public archive of 100 terabytes, and all the version of it over time. And this is something that is entirely not clear to us yet at this point. You can help. So of course, I'm looking forward to an interesting discussion with you on how to face those challenges. But more generally, if you want to get involved, it's pretty standard free software project. So we have our communication channels, public mailing list, public IRC channel. All our code is available on our Forge, which is a Fabricator instance. And the top priorities in terms of development energy, if you want to contribute some development work, is actually, of course, adding listers and loaders for targets that we do not support yet. So we have loaders for Git, we have a work in progress loader for Merkle, we have loader for Subversion, but there are a bunch of version control systems out there. Someone will have to write one for CVS, or for SCCS, or for BitKeeper, or whatever. And same thing for all the hosting places. So we have a lister for GitHub, one for Bitbucket, we have a lister for Fusion Forge, but there are a bunch of other hosting places out there, and we need to have a lister for all of them. We want to have some eye-candy web interface that people can use, and this is something that is not top priority for us, but should be pretty easy to add on top of the existing web API. We have a prototype that is not ready for production yet, so if you are web developer, that's a way to help us out. And of course, you can use your imagination to any kind of content indexing and search on all the content we are covering. So you can join us. So we actually have some job openings available at the time if you are interested in a Paris-based job. And we have also opportunity for students, in case you are in touch with students for summer internship, as usual. We're a pretty small community. So the core team is 4 people. So we are me and Alberto Di Cosmo, co-founder. We have a couple of engineers, Antoine and Nicolas, plus interns that come and go over summer. The project is currently initiated, has been fully funded by INRIA, which is a French research institute with a very strong free software background. They were one of the 3 funding partners of the W3C, so they have a good track record in creating initiatives, then leave the institute and go on as international organizations. And we have a bunch of supporters and partners. Okay? Among our first sponsors, you have Société Générale, you have Microsoft that is offering Azure-based income and resources. We have Nokia, we have Dance, some more to be announced soon. And we have a bunch of organizations, mostly from the scientific and free software international world, that have been expressed their support to what we're doing, and that are all listed on our website, of course. So another way of helping out for making this sustainable in the very long run and remain a non-profit endeavor is, of course, helping us find other supporters and partners for the initiative. This is it for me. I'm really looking forward to your questions and comments, and thanks a lot for having me here today.